Welcome back to Robbie's Office Hours. Today we're talking about phase line stability, part 2. Just another example of an autonomous first order differential equation where we're analyzing the phase line and stability of the corresponding critical points. Okay, so remember, how do we do these? Step 1 is to say find the critical points, which means set the right-hand side equal to 0. So I'm going to look at y times y minus 2 squared times y plus 1 equals 0. Thankfully, this is factored for me, so I get all my roots as being y is 0, y is negative 1, and y is 2. So I get my critical points. These are given by y equals, let's put them in order, so minus 1, 0, and 2. Okay, so those are critical points. And now we're going to look at the phase line. Okay, so the phase line, remember, we have this vertical orientation of this. We draw y equals negative 1. We draw y equals 0. And we draw y equals 2, so something up here, y equals 2. And then we just basically like to say, what is the derivative sign in each of these corresponding intervals, okay? So let's pick something below. So if I choose something y is like negative 2, so if I say y is minus 2, then what is dy dt going to be? Well, let's see. This is going to be negative 2. Okay, this is something squared, which is always positive. So this is negative times positive times negative. So what's negative, positive, negative? That's positive in total. Okay, so that means everything below negative 1 has a positive slope, so the arrow goes up. Okay, remember that indicates a positive arrow, or an arrow pointing upwards, sorry. If y is, let's say, something in between 0 and negative 1, so negative a half, y is minus a half, what do I see? Well, again, this is negative, positive, positive, so negative, positive, positive is negative. So dy dt is negative, which is a downward arrow. So in here, I'm going to have a downward facing arrow. So immediately we know that y equals negative 1 is stable. Okay? If I choose a point above y equals 0, say y equals 1, then what is dy dt in this case? Okay, so that's positive, positive, positive. Okay, so that's good. That's positive. So that's an upward arrow. So that's going to be an upward arrow here. And notice that like y equals 1 wasn't special, right? Like anything above 0 is going to make this positive. Anything above 0 is going to make this positive. And this is always positive no matter what. So we don't even have to check above up here. Okay, I mean, if you want to, you could say like y equals 3 and just check that, well, dy dt is also positive. In that case, so that's an upward arrow. Okay, things like that. But now we can see immediately the stability. Okay, so what's the stability? We're going to say y equals negative 1 is stable. Okay, so that one's stable because on both sides I'm getting sucked into negative 1. Y equals 0 is unstable because on both sides I'm getting pushed away from y equals 0. So y equals 0 is unstable. Okay. And y equals 2 is like semi-stable. Below 2, I'm getting pushed into it. Above 2, I'm getting pushed away. So y equals 2 is semi-stable. Okay? Now, if I wanted to, I could draw sample curves and all this kind of stuff. I'd say, well, below, I'm getting pulled into it kind of thing. I'm getting pushed into it like this. Okay? Up here, I'm getting pushed away. Things like that, maybe. And then up here, I'm getting pushed away like that. Okay? So if we wanted to draw different sample solution curves depending on our initial conditions, we could. That's unnecessary in order to just get the stability of the corresponding critical points. Okay? So hopefully this gives you another example and just more practice on classifying critical points of autonomous first order ODEs. Okay? As always, like, subscribe, share with your friends, comment down below. These are your office hours, guys, so just please ask me questions. All right? We'll keep moving.